Module Title: Chemistry Subject Area Method 1, Module Introduction. Dear student teachers, welcome to this Chemistry Subject Area Method 1 module. I hope you will enjoy this module, because you will see how the theories and concepts of your academic and other professional courses transform into your subject chemistry, which will be helpful to enjoy your endeavor in teaching chemistry. This is true because it blends subject-specific chemistry contents and pedagogical knowledge, skills and dispositions into an integrated whole, the best secret for better chemistry teaching. We believe that you have covered several fundamental principles, concepts, theories, laws and facts of the subject chemistry from your first degree study. Thus, you, as a chemist, have the knowledge, skills and dispositions related to the subject chemistry expected of undergraduate program. Furthermore, you have covered general principles of pedagogy and psychology from the basic courses offered under PGDT programs so far. Now it is time to deal with how to teach chemistry and its proper pedagogy. By integrating your subject area and pedagogical knowledge as the concern of this module. Expected learning outcomes. After completing this module, you will be able to understand the effective methods of teaching chemistry, independently design methods of teaching and experimental activities, evaluate the goals and objectives of secondary school chemistry curriculum, describe the development of chemistry with different portions they are going to teach, explain the steps to be followed in teaching scientific methods in chemistry, compare and contrast an inductive and deductive methods of teaching chemistry, decide on the method to be used for each chapter of high school chemistry, develop attitudes, skill and knowledge of the lessons of the science of chemistry in high school and in their future career. Identify possible difficulties of students in learning chemistry and resolve their problems. Systematically manage the factors affecting teaching/learning chemistry. Organize and develop the mechanism of solving different chemistry problems. Resolve the problem of conceptual understanding of chemistry concepts. Develop proportional reasoning and higher-order thinking skill. Appreciate chemistry as discipline in equipping students with knowledge needed to solve everyday real-world problem. Note to the teacher, the course Chemistry Teaching Methods does not aim at teaching chemistry knowledge or pedagogical knowledge, as there are other courses intending to deal with these subjects. Rather, its ultimate goal is to equip prospective teachers with some hints as to how to find best ways to deal with a given chemistry topic, so that it becomes understandable for students of a certain age and academic level. In fact, this goal may lead us to think about Shulman's Pedagogical-Content Knowledge. Shulman, 1986. Chemistry education is not a mere combination of chemistry and education. It is a field that blends subject-specific chemistry content and pedagogy into an integrated whole, and attempts to provide a coherent response to students. Knowing the subject biology and chemistry does not make a person a professional biochemist. He or she needs to apply the chemistry knowledge into the subject biology or vice versa. Likewise, having a knowledge of chemistry and pedagogy does not make a professional chemistry educator. He or she needs to come up with a pedagogical method as to how to communicate the chemical knowledge to the students, so that the students themselves also devise their own method to transfer the skill, attitude and knowledge or competency. To accomplish this, one needs to have pedagogy-content knowledge (PCK). Commenting on pedagogy-based criteria commonly used for evaluation of teaching, Shulman 1986 asked, "Where did the subject matter go? What happened to the content? Perhaps a productive path for us to travel," is what Shulman has labeled pedagogical content knowledge (PCK). While content knowledge refers to one's understanding of the subject matter, and pedagogical knowledge refers to one's understanding of teaching and learning processes independent of subject matter. Pedagogical content knowledge (PCK) refers to knowledge about the teaching and learning of particular subject matter, taking into account the particular learning demands inherent in the subject matter. Since then, the analytic distinction between teachers' subject matter knowledge and teachers' knowledge of pedagogy has begun to fade, due to Shulman's pedagogical content knowledge. Shulman argued that a distinctive form of teachers' professional knowledge, that he called PCK, exists, and that this form of knowledge builds upon, but is different from, teachers' subject matter knowledge or knowledge of general principles of pedagogy. In Shulman's view, PCK is a form of practical knowledge that is used by teachers to guide their actions in highly contextualized classroom settings. In Shulman's view, this form of practical knowledge entails, among other things, a knowledge of how to structure and represent academic content for direct teaching to students, b. knowledge of the common conceptions, misconceptions, and difficulties that students encounter when learning particular content, and c. knowledge of the specific teaching strategies that can be used to address students' learning needs in particular classroom circumstances. In the view of Shulman and others, pedagogical content knowledge builds on other forms of professional knowledge, and is therefore a critical, and perhaps even the paramount constitutive element in the knowledge base of teaching. In general, knowledge subject content refers to one's understanding of the subject matter, while pedagogical knowledge refers to one's understanding of teaching and learning processes independent of subject matter. Pedagogical content knowledge (PCK) refers to knowledge about the teaching and learning of a particular subject matter, taking into account that the particular learning demands inherent in the subject matter. Therefore, in this module you will deal with the combination of chemistry knowledge and pedagogy knowledge, so that you can be able to present a given topic chemistry to learners who are assumed not to have the idea about the topic, and you should treat each topic in this module chemistry education perspective. In order to ensure your clear understanding of the basic issues, several in-text questions and activities are included, and feedback is provided after each activity. We advise to attempt to give your own response before looking at the feedbacks. This module requires you a minimum of 80 study hours in order to successfully complete your study. We have prepared this working material for you carefully in such a way that you can easily read, understand, and learn the methods of teaching chemistry. Hence, after completing this module, we are very much sure that you will have a good conceptual base for teaching the subject chemistry. Unit 1 Introduction to Chemistry as a Discipline. Unit Introduction. Welcome to the Unit 1 of this module of Methods of Teaching Chemistry. In this unit you begin to study the methods of teaching chemistry, first starting by defining the subject chemistry as a discipline. Then you will pay attention to the importance of the knowledge of chemistry in our individual daily life and the world society as a whole. And finally you move on to a short review of the historical development of the subject chemistry. We believe that you have covered these topics in your career as a chemist, in the high schools and in universities. This is not to teach you as new topics, but to prepare to teach this topic to students in the high schools. You need to treat the topics in chemistry education perspectives. In addition to historical background of chemistry, the part of the unit contains topics covered in high school chemistry. The author of the module tries to see in different mode of approach each topic must be covered fully at one level than two different stages of grade level. To achieve the earning outcomes of this unit, basic conceptual frameworks, principles and facts are presented for you. Besides, a number of in-text questions and activities are included to keep you in track with your efforts of learning. Feedback is provided for you immediately after each activity, so that you can be able to measure your progress. We expect you to do all the necessary tasks presented to you. This unit requires you a minimum of 81 study hours in order to successfully complete your study. Upon completion of the unit, the trainee will be able to identify the basic objective of teaching learning chemistry, analyze the given objectives in chemistry lesson and devise a system how to apply it, explain the contribution of chemistry for social development, integrate the development of chemistry with the topics to be covered, discuss the main applications of chemistry, describe chemistry topics they covered in the university and compile basic topics to be taught in high school chemistry, draw lessons from the summary of the effective and non-effective methods of teaching chemistry they observed, the meaning and nature of chemistry as a discipline. Activity 1.1. How do you define and explain nature? To answer this question, teachers may invite students to observe their surroundings, to explore the elements of nature. Then after, students shall share what they have observed to their peers and the whole class. Nature includes all that exists in the universe. In turn, the universe includes all that exists, whether it can be perceived or not, the Earth and its atmosphere, the planets, star space, etc. You should not reduce the universe to only the things on the Earth and around it, but think far beyond, even beyond the solar system. Nature is very vast, complex and interconnected. It is this vast area that science is dealing with. One of the qualities of human being is to his or her interest to know inside or composition of something. Carefully observe your surrounding, a tiny portion of nature where you are now. In-text question 1.1. 1. Think about natural world around you. What general forms of nature do you observe? 2. In your day-to-day activities you usually use the word science. What do you mean when you say science? The components which constitute the whole nature can be classified based on the criteria of the presence of mass matter and the absence of mass non-matter, which usually include forms of energy. It is we human beings who classify nature as matter, and a non-matter, but they do not exist independent of each other. The forms of nature may or may not be detected by our senses. That is, some forms of matter are extremely small that they may not be detected by our senses nor by instruments. This does not mean that extremely small particles do not exist, but it is our incapability to detect them. Human being has been interacting with nature since antiquity. Human being has unique capacity of logical thinking relating cause and effect. With this special quality, human observes nature with the help sense organs as well as instruments. Through the process of observation, human collects information about all things and phenomena around. Using the capacity of logical thinking, human being logically rationalizes, explains, and interprets and corrects the information obtained through observation about nature. In this process, human being gets understanding nature and creates a mental picture about relationships and regularities in nature. The understanding being made is organized or systematized in the mind. This systematized understanding about nature constitutes knowledge. It is this systematized knowledge that is named as science. This science is the systematized knowledge of human being about nature which is acquired through experimentation, interpretation, correlations, and rationalizations of several observations about nature. In short, science is knowledge about nature. The observation, identification, description, experimental investigation, scientific method, and theoretical explanation of phenomena. Such activities are restricted to a class of natural phenomena and applied to an object of inquiry or study. Activity 1.2. Why is it necessary to study science and its branches? First, invite students to examine the different outcomes so far achieved in science, in improving the welfare of human beings. Then, in doing so, make students understand the why of studying science. You can use inductive teaching to help students understand the question. The knowledge about nature is extremely vast because the subject nature is very complex. One person cannot study and handle all information about nature during his or her lifespan. As a result, science has evolved into a number of closely related broad as well as specialized categories of knowledge. In the same line of thinking, chemistry has appeared as one of those specific fields of knowledge about nature. That is, chemistry is a class of knowledge about nature, and it overlaps with most of other branches of sciences. Activity 1.3. Mention the objectives of teaching the subject chemistry at secondary school level. I should like to begin by recording a number of depressing facts about science education over the past 10 years in Ethiopia. The facts are very pessimistic, but realistic. Most schools are struggling to find qualified and competent staff. In lower classes, grade 7 and 8, chemistry teachers are not graduates of chemistry. The laboratory are missing or ill-equipped with material and human resource. Research literature has been dominated by work on misconceptions, but little has yet appeared about how to reverse these, or to avoid them altogether. The general public has little knowledge of chemistry and its application, and encourage his or her children to other attractive disciples. The organization of the text, setting of examination, laboratory activities and the teaching method in general is traditional and little has changed for the last 50 years. Section 1.2. The objectives of learning teaching chemistry. Chemistry is one of the most important branches of science. It enables you to understand what happens around you. Chemistry as a science has started very long years ago and has been a constant companion of human beings since antiquity. There is no human activity that does not involve the basic ideas and skills of chemistry. This it is as old as human being. All present world civilization has been based on the basic principles of chemistry. Chemistry is one field of natural science that deals with part of nature, matter, and specifically concerned with the study of properties, composition, structure, transformation and energy associated with the changes of matter at atomic, ionic, and molecular level. In this definition is implied that chemistry builds up on the explanation of the bulk matter starting from the atoms, subatomic particles, ions and molecules. This definition seems routine for you who has been exposed to elementary chemistry lessons in high schools and advanced courses in a university. Nevertheless, it clearly fixes the philosophy, the direction of thinking of chemistry, to learn and to teach. Especially what is to be underlined in the philosophy of chemistry is thinking and explaining matter at atomic, ionic, molecular level, which means that chemistry is a microscopic subject. Then, when you study or teach chemistry, this is the general framework, playground, where you have to work. The critical issue of this course, methods of teaching chemistry, is not to explicitly deal with subject chemistry itself, but major objective of this course is chemistry educations, which means to design the best ways to share or transmit the accumulated understanding of matter by human being at microscopic level so far to the target individuals, maybe children, college students, or adults within the general public. During the 19th century, chemistry was introduced into high schools to fill a vocational, rather than an intellectual need. It was not until the 20th century that it was recognized as a subject that could contribute to the training of the mind. Activity 1.4. Consult different sources of information such as friends, teachers or different reference materials from library or internet and answer the following questions. 1. What is the distinction between chemistry through education and education through chemistry? 2. Which one shall we follow during chemistry teaching in schools? Why? The following table gives a comparison illustrating the differences in emphasis between chemistry through education and education through chemistry. Chemistry through education. Learn the chemistry knowledge and concepts, theories and laws. Undertake the processes of chemistry through inquiry learning. Gain an appreciation of the nature of sciences. Undertake practical work and appreciate the work of scientists. Develop positive attitudes towards chemistry and scientists. Acquire communicative skills related to oral, written and symbolic/tabular/graphical formats. Undertake decision-making in tackling scientific issues. Apply the uses of chemistry to society, becoming chemistry-related careers. Education through chemistry. Learn fundamental chemistry knowledge, concepts important for understanding and appreciating socio-scientific issues within society. Undertake investigatory scientific problem solving to better understand the chemistry background related to socio-scientific issues within society. Gain an appreciation of the nature of sciences. Develop personal skills related to creativity, initiative, safe working, etc. Develop positive attitudes towards chemistry as a major component in the development of society and scientific endeavors. Acquire communicative skills related to oral, written and symbolic/tabular/graphical formats. Undertake socio-scientific decision-making related to issues arising from the society. Develop social values related to scientists. A responsible citizen and undertaking scientists. Chemistry is one of the most important branches of science. It enables learners to understand what happened around them. Because chemistry topics are generally related to, or based on the structure of matter, chemistry proves a difficult subject for many students. Chemistry curricula commonly incorporate many abstract concepts, which are central to further learning in both chemistry and other sciences. Chemistry, by its very nature, is highly conceptual. While much can be acquired by rote learning, this often being reflected by efficient recall in examination questions, real understanding demands the bringing together of conceptual understandings in a meaningful way. Further, chemistry curricula traditionally focus on learning fundamental chemical concepts and pay little attention to other important aspects of scientific literacy, which might encourage memorization and rote learning instead of meaningful learning. In the Ethiopian educational system, science teaching is mainly separated from the actual application it can provide for the society. However, the suggestion is that the teaching of a sequence of chemistry lessons begins from a relevant socio-scientific context. Two important skills are addressed in teaching for relevant scientific problem-solving and socio-scientific decision-making. The teaching progresses from the societal, the familiar, to the chemistry concepts, the unknown, which are needed to better appreciate the issues or concerns, and then proceeds to the socio-scientific decision-making needed. Chemistry fundamentals, grouping chemistry concepts for scientific convenience rather than for popularity, are not the approaches to promote education through chemistry. Such an approaches lead to an academically perceived course that is likely to be abstract, difficult, and irrelevant. Important point: the timeline of chemistry lists important works, discoveries, ideas, inventions, and experiments that significantly changed human understandings of chemistry. Looking at this will help us to appreciate how previous people transferred their wisdom through education to the present society, and which is also helps us to be conscious about our duties in chemistry education, to transfer the past and present knowledge of chemistry to forthcoming generation. Section 1. 3. Contribution of chemistry for development. In-text question 1.2. 1. Can you list processes that involve chemical knowledge in your daily life? 2. Can you mention any science-related field of study that chemistry is not given as a subject, or some basic concept of atomic structure is not applied? Chemistry contributes to our existence, our culture, and our quality of life. Chemistry is concerned with the changes we see around us: the air, the soil, the water, rusting of iron, bad smell of wastewater, decay of living things, burning of wood, and many more. A plant takes carbon dioxide from the air and water from the soil to produce carbohydrates and oxygen through a wondrous series of chemical reactions called photosynthesis. All living processes are chemical reactions. Everything we use, wear, live in, ride in, and play with is produced through controlled chemical reactions. Chemists design reactions that will convert chemical substances we find around us into chemical substances that serve our needs. Urea fertilizer is produced from nitrogen and hydrogen, and many other substances with controlled reactions in an industry. Chemistry answers the needs of our society through a deep understanding of the factors that govern and furnish control of chemical reactions. It plays a critical role in man's attempt to feed the world population, to tap new sources of energy, to clothe and house humankind, to provide renewable substitutes for dwindling or scarce materials, to improve health and conquer disease, and to monitor and protect our environment. Because of this responsiveness to human needs, chemistry has become a crucial factor in the nation's economic well-being. Since all life processes are brought about by chemical changes, understanding chemical reactivity is a vital foundation for our ultimate understanding of life. Thus, chemistry, along with biology, contributes to human knowledge in areas of universal philosophical significance. All aspects of our life: food, clothing, shelter, hygiene, health, transportation, lighting, heating, entertainment, etc., are influenced by chemistry. Activity 1.5. Make small group and list the important materials that were made accessible to human beings as a result of application of the knowledge of chemistry in agricultural production, health, clothing, shelter, transportation, and energy source. Remember, you can use the following list of applications of chemistry as a comment or feedback for the activities. 1. The tablets, capsules, and injections you take when you are ill are prepared through understanding of the chemical processes. 2. Fertilizers, insecticides, and pesticides have been developed by chemists. This has led to an increase in the production of food. These developments have been responsible, to a large extent, for the success of the Green Revolution in India. 3. Detergents, soaps, cosmetics, and perfumes are mostly products of the knowledge in chemistry. 4. Durable and crease-resistant synthetic fibers like nylon, rayon, and terylene have been developed through the processes of chemistry. 5. Plastic products, paints, synthetic rubber, glass, and fuels for cars, aeroplanes, and rockets are all gifts of chemistry. Applications of chemical science have contributed significantly to the advancement of human civilization. With a growing understanding and ability to manipulate chemical molecules, the post-World War I chemist was considered a societal problem solver. They synthesized crop-enhancing agricultural chemicals to ensure a constant and viable food supply. They played a significant role in the eradication of deadly diseases by developing life-saving pharmaceuticals and chemical pesticides. Chemists also developed innovative plastics and synthetic fibers for use in both industrial and consumer products. The chemical industry has been a vital sector of the modern industrialized economy. Section 1. 4. Development and present position of chemistry. In-text question 1.3. When was chemistry considered as a science? What were the reasons that made chemistry to be considered as a science? The Greeks were the first people to put forward scientific ideas concerning the origin of changes they saw in the physical world. From the time of Thales, about 600 BC, who assumed that all substances were derived from water. The other Greeks, such as Empedocles, 450 BC, expanded the idea of Thales to the four elements theory of substances. Empedocles assumed that every substance made up of four elements: fire, air, earth and water. About 450 BC, Democritus proposed the idea of atoms, which means indivisible, and he forged the theory of discontinuity or the principles of discreteness. And he stated that all substances made up of atomos atoms. Aristotle 384–322 BC suggested that in addition to the four basic elements there could be two pairs of opposite qualities: hot-cold, wet-dry, and cold-dry, wet-hot, dry-hot, and cold-wet. In-text question 1.4. What were the major objectives of alchemy? Were they successful in the experiments to attain their objectives? What were the important outcomes of alchemists that influenced our thinking about the change of matter? The era of alchemy started around 540 BC and lasted to the end of 17th century by English chemists. Roughly the period 1500 AD to 1650 AD is sometimes known as the era of medical chemistry. Generally speaking, alchemy aimed at the great human goods: wealth, longevity, and immorality. The practice of alchemy continued for more than 2,000 years. Gradually the theories and attitude of the alchemists began to be questioned. The alchemy died and modern chemistry emerged because of curious people started to ask more interested questions about matter. In-text question 1.5. How would you define an experiment? How would you explain the scientific method? Robert Boyle, 1627–1691, an English chemist and physicist, saw the shortcoming of alchemy. Studies about the properties of gases with careful experimentation, which is considered as the beginning of chemistry. George Ernest Starr, 1660–1734, put forward the phlogiston theory, with which he believed that when a substance burns, it gives off its combustible part to the air. He called phlogiston from Greek word for inflammable. The British chemist Joseph Priestley's 1733–1804 discovery of oxygen as a component of air and its ability to support combustion brought about the end of phlogiston theory. In-text question 1.6. During the early development of chemistry, solids have been relatively easily discovered compared to gases. Why gases were discovered later? Briefly explain the experiment that Priestley and Lavoisier carried out during their discovery of oxygen. Priestley informed the French scientist Antoine Lavoiser, 1743–1794, of his discovery of oxygen. Lavoisier immediately repeated Priestley's experiments and found that oxygen was truly formed Then he performed his own experiment. He has burned substances and weighted both the combustibles and their products. He has proved that when metals corrode, their mass increases. Also he showed that the apparent loss of mass accompanying the burning of a substance such as wood is merely the result of the product of the combustion being gaseous. And he showed that oxygen, not phlogiston, supported combustion. As a result, Lavoisier formulated and stated one of the fundamental laws in chemistry, the law of conservation of mass. Activity 1.6. How would you state the law of conservation of mass? When wood is burned, is mass conserved? If magnesium is burned, is mass conserved? Which one of the above reactions will be simple to demonstrate the law of conservation of mass? Why? Use group discussion. It states that the total mass of materials present after chemical reaction is the same as the total mass of materials before the reaction. Lavoisier is considered the father of chemistry. His book, Elementary Treatise on Chemistry, published in 1789, indicated to the world that chemistry is a science based on theories supported by reproducible experiments. In 1803, an English chemistry teacher, John Dalton, proposed atomic theory of matter by extending the assertion of the ancient Greek philosopher, Democritus. In-text question 1.7. 1. What were the bases from previous development of chemistry for Dalton to propose his atomic theory? 2. Describe Dalton's atomic theory and compare it with the currently used modern atomic theory of matter. In 1808, the French chemist and physicist Joseph Gay-Lussac showed gases react with one another. They do so by volumes in the ratio of small whole numbers. Around 1811, the Italian physicist Amado Avogadro was able to reconcile Dalton's atomic theory with Gay-Lussac's law of combining volumes. In his hypothesis stated that equal volume of different gases at the same temperature and pressure contains the same number of molecules. In 1828, a German chemist, Friedrich Wholer, synthesized urea from inorganic salts, which makes the beginning of organic chemistry. In 1869, Dmitry Ivanovich Mendeleev forwarded the periodic law states that the properties of elements are periodic function of their atomic masses. In 1894 to 1897, J.J. Thomson conducted a series of investigation which led him to the discovery of electrons. From the turn of the 19th century to the discovery of other subatomic particles paved the way for the dramatic progress of chemical science and technology. Section 1.5. The 4 chronological categories in the development of chemistry. Chemistry owes much of its CAR1Y development to alchemy. Alchemists were not perceived to be true scientists, but rather magicians or mystics. By the 15th century, their efforts were chiefly focused in two areas: finding a cure for diseases and discovering a way to turn base metals into gold. As the scientific revolution spread, sparked by the works of Galileo and Newton, and later Lavoisier in chemistry, the practice of alchemy ceased. From black magic to modern era, the development of chemistry can be grouped to 4 categories: black magic, alchemy, traditional era and modern era. Assignment: using available sources of information such as related literature, senior chemistry teachers and etc. Compile and present a short report of your collection about the historical development of chemistry. Subsection 1.5.a. The Black Magic. The history of chemistry is often divided into 4 periods: black magic, alchemy, traditional chemistry and modern chemistry, 20th century chemistry. Prehistoric times to the beginning of the Christian era. This was the era in which Sumerian, Babylonian, Egyptian and Greek cultures were flourishing. During most of this period, mysticism and superstition prevailed over scientific thought. In this era, most people believed that natural processes were controlled by spirits, and they relied upon magic to persuade the spirits to help in their favor. Very little chemical knowledge was gathered, but some elements such as iron, gold, and copper were recognized. During this time, the Greek philosophers Thales and Aristotle speculated on the composition of matter. They believed that earth, air, fire and water, some others imagined a fifth substance known as quintessence, were the basic elements which composed all matter. Toward the end of this era, people learned that iron could be made from dirty brown earth and rock, and that bronze could be made by combining copper and tin. This led many to believe that, if yellowness and hardness could be combined, gold would be formed. This belief that gold could be formed from other substances led to a new era known as alchemy. Subsection 1.5.b. The alchemy. Chemistry emerged to develop as alchemy in ancient Alexandria, Egypt. The alchemy period lasted from 540 BC to 177 AD, the beginning of the Christian era, to mid-17th century. During this long era, many alchemists believed that metals could be converted to gold with the aid of a mystical thing called a philosopher's stone. The philosopher's stone was never found. However, many discoveries of new elements and compounds were made during this period. In the early 13th century, alchemists like Roger Bacon, Albertus Magnus and Raymond Lully began to realize that the search for a philosopher's stone was futile. They believed that alchemists would better serve the world by discovering new products and new methods to improve everyday life. This started a trend in which alchemists gave up on finding the philosopher's stone. An important leader in this movement was a Swiss by the name of Theophrastus Bombastus. Bombastus felt that the object of alchemy should be the cure of the sick. He believed that salt, sulfur, and mercury would give health if they were present in the body in proper proportions. This was the first period of vitrochemistry. The last influential chemist in this era was Robert Boyle. In his book, The Sceptical Chymist, Boyle rejected the leading scientific theories of his day and started the list of elements which are still recognized today. He also formulated a law relating to the volume and pressure of gases. See Boyle's law. In 1661 he founded a scientific society which later became known as the Royal Society of England. Even though the alchemists never achieved their principal goals, they did uncover a vast amount of chemical change. Various contemporary techniques and glasswares are traced the alchemists. Subsection 1.5.c. Traditional chemistry. The MJD 17th century to mid-19th century. By this time, scientists were using modern method of discovery, by testing theories with experiments. One of the great controversies during this period was the mystery of combustion. The traditional chemistry era can be described by the following events. 1. Phlogiston theory states that, when a substance is burned, phlogiston was supposedly added from the air to the flame of the burning object. In some substances, a product is formed. 2. Coulomb's law: given two particles separated by a certain distance, the force of attraction or repulsion is directly proportional to the product of the two charges, and inversely proportional to the distance between the two charges. 3. Disproving of Phlogiston Theory: Joseph Priestley heated calx of mercury, collected the colorless gas and burned different substances in the colorless gas. He called the gas dephlogisticated air, but it was actually oxygen. It was Antoine Lavoiser, father of modern chemistry, who disproved the phlogiston theory. He renamed dephlogisticated air oxygen, when he realized that oxygen was the part of air that combines with substances as they burn. Traditional chemistry is different from traditional chemists. Do you know the difference between the two? Traditional chemists currently hold power and position in universities and industries, and currently establish legitimization of principles. They rely on instrumental rationality, success determined by citations, power maintained by senior professors and chemists. Data is sometimes published in whole or part depending on funding source. Lab notebook and data owned by private laboratory or company, etc. In addition to the above facts, most of our traditional professors lack multidisciplinary collective research project that could alleviate problems of the society. Section 1.5. Modern era chemistry. During the 19th century, chemistry was introduced into high schools to fill a vocational, rather than an intellectual need. It was not until the 20th century that it was recognized as a subject that could contribute to the training of the mind. Mid-19th century to present, this is the era chemistry flourished. Lavoisier's thesis gave chemists the first sound understanding of the nature of chemical reactions. Lavoisier's work led an English school teacher by the name of John Dalton to formulate his atomic theory. Around the same time, an Italian chemist, Amedeo Avogadro, formulated his own theory, Avogadro's law concerning molecules and their relation to temperature and pressure. By the middle of the 19th century, there were approximately 60 known elements. John A. R. Newlands, Stanislaw Knizerow and A. E. B. de Chanketois first noticed that all of these elements were very much alike in structure. Their work led Dmitry Mendeleev to publish the first periodic table. Mendeleev's work set the foundation of theoretical chemistry. In 1896, Henri Becquerel and the Curies discovered the phenomenon known as radioactivity. This laid the foundation for nuclear chemistry. In 1919, Ernest Rutherford became discovered that elements could be transmutated. Rutherford's work laid the basis for interpreting the structure of the atom. Soon after, another chemist, Niels Bohr, finalized the atomic theory. These and other major advances in chemistry have led to many distinct branches of chemistry. These branches include, but are not limited to, biochemistry, nuclear chemistry, chemical engineering, Organic chemistry. In-text question 1.8. In the above section, the development of chemistry from traditional to modern era was explained through scientists such as John Dalton and Antoine Lavoiser. Are there other chemists that contribute for development of chemistry? Mention at least 4 chemists and present their contributions to the development of chemistry. What are important discoveries of the modern era of chemistry? Give specific time of the discovery, events, and description of each event. Section 1.6. Categorizing high school chemistry contents into different fields of chemistry. Activity 1.7. You are entailed to go through the contents from grade 9 to 12 textbooks of chemistry and see the number of units at each grade level. Then, identify similar or same topics repeated across the grades, and if you were given an assignment to organize the content, what possible option of arranging the contents do you propose? Discuss the validity of the content for the learner. Make a group of 5 and take 15 minutes to come up for possible order of contents. The next, and most recent, curriculum directions in science and chemistry education have been influenced largely by questioning the process of learning and, in particular, by research on what was being taught and whether it was being learnt. Piaget asserted that the child did not acquire knowledge merely by being told or by reading about it, rather that the child must act on the knowledge. In the late 1970s and early 1980s, research projects in several countries were established to investigate children's learning in science. All of the studies clearly demonstrated that children's learning in science is an investigative, constructive process. Research in this field seeks, in various contexts, to define conditions that promote optimal students' inquiry and the teaching that can provide those conditions. The general philosophy that supports this view has come to be called constructivism. Many cognitive scientists now believe in a constructivist model of knowledge that attempts to answer the primary question of epistemology: how do we come to know what we know? This constructivist model can be summarized in a single statement: knowledge is constructed in the mind of the learner. In the constructivist model, students are perceived as active learners who come to chemistry lessons with preconceived ideas about natural phenomena which they use to make sense of their everyday experiences. Good science education is true to the child, true to life, and true to science. Based on the above ideas, a given curriculum is valid if it fulfills the following criteria. Cognitive validity requires that the content, process, language, and pedagogical practices of the curriculum are age-appropriate and within the cognitive reach of the children. Content validity requires the curriculum must convey significant and correct scientific content. Process validity requires the curriculum engage the learner in acquiring the methods and process that leads to generation and validation of scientific knowledge, and nature and natural curiosity and creativity of the child in science. The process validity is an important criteria since it helps the student in learning to learn science. Environmental validity requires that science be placed in the wider context of the learner's environment, local and global, enabling him or her to appreciate the issues at the interface of science, technology, and society, and preparing him or her with the requisite of knowledge and skills to enter the world of work. Ethical validity requires that the curriculum develop in the learner a concern for life and preservation of the environment. Considering the Ethiopian curriculum, much effort was exerted to make it attractive in form and content. The activities and experiments are also incorporated to make learning attractive. From my personal experience, our high school students do not relate the classroom practice with the real world. This could be due to the curriculum design, or mainly due to lack of capacity and commitment of the teaching staff. Chemistry is traditionally divided into subdisciplines including analytical, inorganic, organic, and physical chemistry. The division between disciplines has no cross-cutting border and make it difficult to group. I strongly believe the portions to be covered at this level will be very important topics for any disciple in chemistry. Therefore, the topics should be considered as basic chemistry topics and can be used in all studies of chemistry and related subjects such as biology, physics, medicine, agriculture, etc. When you refer the chemistry content from grade 9 to 12 in Ethiopia high schools, you may find the following facts. Grade 9 and grade 11 chemistry content have two similar chapters with similar topics which can be discussed together: chemical bonding and intermolecular forces and chemical bonding and structure. Grade 10 and grade 12 content has one identical topic, electrochemistry, which can be studied at grade 10 level, and one similar topic, chemistry in industry and environmental pollution, and some elements in nature and industry. Periodic classification is the first chapter, and atomic structure and periodic table is discussed at grade 11. The concept is even introduced in grade 8 chemistry syllabus, and there is no need to discuss at grade 11. The topic can be discussed at grade 9 only. The fundamental concepts in chemistry is treated in grade 11, which should come at the beginning of the high school grade 9. The importance of inorganic compounds is related to industrial application and can be part of the topic. The arrangement of content seems confusing and lacks logical flow. You study the atomic structure in grade 9, and after 2 years, you are asked to remember the topic to understand new information at grade 11. The topic Introduction to Organic Chemistry is introduced for grade 10 students at the beginning. The last chapter in grade 11, carboxylic acids, esters, fats and oils, needs a previous knowledge of organic chemistry. Polymers in grade 12 also needs the concept of both chapters from grade 10 and 11. Such arrangement may create knowledge gap and makes understanding of the topics difficult. The topic Chemistry in Industry and Environmental Pollution in grade 10, and the topic Some Elements in Nature and Industry in grade 12 can be grouped together as a topic, rather than separate topics at different class level. The level or complexity of the topics is not different, and placing the topic at different level has very little justification. As a chemist and environmentalist, I prefer to study the nature and industrial application before knowing environmental issues. I strongly believe that similar topics must be grouped together, and arrangement of topics should follow logical ordering of the topics, and grouping topics with similar ideas could facilitate the understanding of the subject chemistry. One can suggest possible arrangement of topics in logical order, and specific topic could be completed at one stage by avoiding unnecessary repetition. Chapter 1. Periodic Table and Atomic Structure. The periodic table displays the elements in increasing atomic number and shows how periodicity of the physical and chemical properties of the elements relates to atomic structure. As a basis for understanding this concept, students know in this chapter how A. to relate the position of an element in the periodic table to its atomic number and atomic mass, B. to use the periodic table to identify metals, semi-metals, non-metals, and halogens, C. to use the periodic table to identify alkali metals, alkaline earth metals and transition metals, trends in ionization energy, electronegativity, and the relative sizes of ions and atoms. D. to use the periodic table to determine the number of electrons available for bonding. E. the nucleus of the atom is much smaller than the atom, yet contains most of its mass. F. to use the periodic table to identify the lanthanide, actinide, and G. transactinide elements, and know that the transuranium elements were synthesized H and identified in laboratory experiments through the use of nuclear accelerators. I. to relate the position of an element in the periodic table to its quantum electron configuration and to its reactivity with other elements in the table. K. the experimental basis for Thomson's discovery of the electron, Rutherford's nuclear atom, Millikan's oil drop experiment, and Einstein's explanation of the photoelectric effect. L. the experimental basis for the development of the quantum theory of atomic structure, and the historical importance of the Bohr model of the atom. M. that spectral lines are the result of transitions of electrons between energy levels, and that these lines correspond to photons with a frequency related to the energy spacing between levels by using Planck's relationship. Chapter 2. Chemical Bonds and Intermolecular Forces. Biological, chemical, and physical properties of matter result from the ability of atoms to form bonds from electrostatic forces between electrons and protons, and between atoms and molecules. As a basis for understanding this concept, students know how A. atoms combine to form molecules by sharing electrons, to form covalent or metallic bonds, or by exchanging electrons to form ionic bonds. B. chemical bonds between atoms and molecules such as H2, CH4, NH3, HCCH2, N2, Cl2, and many large biological molecules are covalent. Sea salt crystals, such as NaCl, are repeating patterns of positive and negative ions held together by electrostatic attraction. D. the atoms and molecules in liquids move in random pattern relative to one another, because the intermolecular forces are too weak to hold the atoms or molecules in a solid form. E. to draw Lewis dot structures and predict the shape of simple molecules and their polarity from Lewis dot structures. F. electronegativity and ionization energy relate to bond formation. G. to identify solids and liquids held together by van der Waals forces or hydrogen bonding, and relate these forces to volatility and boiling/melting point temperatures. Chapter 3. Conservation of matter and stoichiometry. The conservation of atoms in chemical reactions leads to the principle of conservation of matter and the ability to calculate the mass of products and reactants. As a basis for understanding this concept, students know how A. to describe chemical reactions by writing balanced equations. B. the quantity 1 mole is set by defining 1 mole of carbon-12 atoms to have a mass of exactly 12 grams. C. 1 mole equals 6.02 x 10^23 particles, atoms or molecules. D. to determine the molar mass of a molecule from its chemical formula and a table of atomic masses, and how to convert the mass of a molecular substance to moles, number of particles, or volume of gas at standard temperature and pressure. E. to calculate the masses of reactants and products in a chemical reaction from the mass of one of the reactants or products and the relevant atomic masses. F. to calculate percent yield and theoretical yield in a chemical reaction. G. to identify reactions that involve oxidation and reduction, and how to balance oxidation-reduction reactions. Chapter 4. Gases and their properties. The kinetic molecular theory describes the motion of atoms and molecules and explains the properties of gases. As a basis for understanding this concept, students know A. the random motion of molecules and their collisions with a surface create the observable pressure on that surface. B. how the random motion of molecules explains the diffusion of gases. C. how to apply the gas laws to relations between the pressure, temperature, and volume of any amount of an ideal gas, or any mixture of ideal gases. D. the values and meanings of standard temperature and pressure (STP). E. how to convert between the Celsius and Kelvin temperature scales. F. there is no temperature lower than 0 Kelvin, absolute zero temperature. G. the kinetic theory of gases relates the absolute temperature of a gas to the average kinetic energy of its molecules or atoms. H. how to solve problems by using the ideal gas law in the form PV equals nRTI, how to apply Dalton's law of partial pressures to describe the composition of gases and Graham's law to predict diffusion of gases. Chapter 5. Acids and bases. Acids, bases, and salts are three classes of compounds that form ions in water solutions. As a basis for understanding this concept, students know A. the observable properties of acids, bases, and salt solutions. B. acids are hydrogen ion donating and bases are hydrogen ion accepting substances. C. strong acids and bases fully dissociate, and weak acids and bases partially dissociate. D. how to use the pH scale to characterize acid and base solutions. E. the Arrhenius, Bronsted-Lowry, and Lewis acid-base definitions. F. how to calculate pH from the hydrogen ion concentration. G. buffer stabilize pH in acid-base reactions. Chapter 6. Solutions. Solutions are homogeneous mixtures of two or more substances. As a basis for understanding this concept, students know A. the definitions of solute and solvent. B. how to describe the dissolving process at the molecular level by using the concept of random molecular motion. C. temperature, pressure, and surface area affect the dissolving process. D. How to calculate the concentration of a solute in terms of grams per liter, molarity, parts per million, and percent composition. E. The relationship between the molality of a solute in a solution and the solution's depressed freezing point or elevated boiling point. F. How molecules in a solution are separated or purified by the methods of chromatography and distillation. Chapter 7. Chemical Thermodynamics. Energy is exchanged or transformed in all chemical reactions and physical changes of matter. As a basis for understanding this concept, students know: A. How to describe temperature and heat flow in terms of the motion of molecules or atoms. B. Chemical processes can either release exothermic or absorb endothermic thermal energy. C. Energy is released when a material condenses or freezes, and is absorbed when a material evaporates or melts. D. How to solve problems involving heat flow and temperature changes, using known values of specific heat and latent heat of phase change. E. How to apply Hess's law to calculate enthalpy change in a reaction. F. How to use the Gibbs free energy equation to determine whether a reaction would be spontaneous. Chapter 8. Reaction rates. Chemical reaction rates depend on factors that influence the frequency of collision of reactant molecules. As a basis for understanding this concept, students know: A. The rate of reaction is the decrease in concentration of reactants, or the increase in concentration of products with time. B. How reaction rates depend on such factors as concentration, temperature, and pressure. C. The role a catalyst plays in increasing the reaction rate. D. The definition and role of activation energy in a chemical reaction. Chapter 9. Chemical equilibrium. Chemical equilibrium is a dynamic process at the molecular level. As a basis for understanding this concept, students know: A. How to use Le Chatelier's principle to predict the effect of changes in concentration, temperature, and pressure. B. Equilibrium is established when forward and reverse reaction rates are equal. C. How to write and calculate an equilibrium constant expression for a reaction. Chapter 10. Organic chemistry. The bonding characteristics of carbon allow the formation of many different organic molecules of varied sizes, shapes, and chemical properties, and provide the biochemical basis of life. As a basis for understanding this concept, students know: A. The bonding characteristics of carbon that result in the formation of a large variety of structures ranging from simple hydrocarbons to complex polymers and biological molecules. B. Large molecules polymers, such as proteins, nucleic acids, and starch, are formed by repetitive combinations of simple subunits. C. The amino acids are the building blocks of proteins. Chapter 11. Industrial chemistry. The topic will include the study of elements and compounds used as important industrial raw materials. It also includes the role of chemistry in an industry and environmental issues due to chemicals produced in the modern world. Students will study the existence, preparation, and production, use, handling, and storage of important industrial chemicals. For example, CaCO3 is cheap raw material for cement production. It is also used for acid soil treatment. However, due to poor handling, hydrolysis of lime could take place before application and affect the fertility of soil by reducing organic matter content. The chapters mentioned above from 1 to 11 can be grouped from grade 9 to 12 in that order. The possible coverage of the portions in each grade level will be as follows: Grade 9, Periodic Table and Atomic Structure, Chemical Bonding and Intermolecular Forces, Conservation of Matter and Stoichiometry. Grade 10, Gases and Their Properties, Acids and Bases, Solutions. Grade 11, Chemical Thermodynamics, Reaction Rate, Chemical Equilibrium. Grade 12, Organic Chemistry, Industrial Chemistry. Unit Summary. Philosophical attempts to rationalize why different substances have different properties, color, density, smell, exist in different states, gaseous, liquid, and solid, and react in a different manner when exposed to environments, for example to water, or fire or temperature changes, led ancient philosophers to postulate the first theories on nature and chemistry. Chemistry is one of the most important branches of sciences. It enables learners to understand what happened around them. Because chemistry topics are generally related to, or based on the structure of matter, chemistry proves a difficult subject for many students. Chemistry curricula commonly incorporate many abstract concepts, which are central to further learning in both chemistry and other sciences. Chemistry plays a very significant role in today's society. Without chemistry, modern advances would be nearly impossible. Different forms of chemistry are applied every day in order to receive different results in the subject matter. Whether chemistry is involved in pharmaceuticals, forensic science, or agricultural means, chemistry is responsible for advances in these fields, and many others as well. The arrangement of topics in our educational system seems more traditional, and repetition of the same topics at different levels, which has very little justification. Grouping similar topics at the same level could facilitate the understanding of the portions and save time to cover the portion. Assessments mechanism. The following project activities are set to assess your learning of contents covered in this unit. Form a group of 5 students and do the following activities and report your work to the class. 1. Prepare a term paper of not more than 5 pages on the historical development of chemistry and its implications to chemistry education. Each student will present the report in the class. 2. Review the existing chemistry curriculum and comment on its vertical arrangement. You may take the same topic treated in grade 9 and grade 11, e.g. atomic structure, or grade 10 and 12, e.g. electrochemistry. 3. Based on your review of activity 2, suggest whether some of the topics like atomic structure in grade 9 and grade 11 can be completely treated in grade 9 instead of following the existing pattern. Give reasons for your suggestion.